Okay, let's get started. All right. Sorry, the Monday and Wednesday labs are long now with the protein. We finished probably 5 minutes late, so gosh, lost 7 minutes of lecture, so I'll keep you 15 minutes longer. No. I'll make sure to end on time. Okay, I think we talked about these first three last time. So what are common methods to determine mono, di, and oligosaccharides? I hope you guys are studying for the quiz. Axel, go ahead. Different types of chromatography. We can use normal, reverse phase, anion, cation exchange chromatography. That's one. What another type of methods we can use? Enzymatic methods that are very specific to certain substrates. Very good. There's one more class of methods. Go ahead, Grace. Calorimetric methods that are based mostly on the reducing power of the sugars. Okay, great. What is the basis of carbohydrate analysis using enzymes? So what's the basis, meaning how would you use enzymes to determine amount of carbohydrates? The principle of that. Nothing? I've got nothing? Okay, so basically when I ask such a question, what I mean is enzymes, they catalyze a reaction and either the substrate or the product will absorb light. So basically we're measuring always absorption when we're using enzymes. Oftentimes we need two enzymatic steps or reactions to get to a product or the substrate in the second reaction would absorb light. So if your product in the second reaction absorb light, so the higher absorbance correlates with higher concentration. If the substrate of the second reaction absorb light, the lower absorbance correlates with higher concentration. So, and we always need to use standard curve. We always have to use whatever carbohydrate we're trying to analyze as a standard curve. Okay. Oh, by the way, we have updated your grades on the Canvas, so please have a look. If you have any question, I'm happy to meet with you individually and go over any concerns you have. Just want to say that. We did post participation points. Usually I don't post them until the end, but they are posted. And you can look at them. Even if you participated and you save us sometimes when we need somebody to say something, that counts. I do have 20 points of involvement in the class and how active you are and how present you are. Even if you meet your participation points, that's fine. Okay. So moving on, polysaccharides analysis. So we did mono, di, and oligosaccharides. Now there are the larger components of carbohydrates and the major components, which are the starch and dietary fiber. So for starch, commonly we use total starch assay to determine the total starch amount. Or we are interested in looking at degree of gelatinization or degree of retrogradation. Sometimes these assays are done to determine the impact of processing. And sometimes we really want starch to gelatinize. So we see if we look into our processing and see if we caused gelatinization of the starch or the process was not adequate for gelatinization. Degree of retrogradation, sometimes retrogradation is needed, sometimes it's not wanted. So determining degree of retrogradation is part of quality assessment for the starch in a processed food. Okay, and dietary fiber, there are methods to determine total dietary fiber, and sometimes we are only interested in pectin. We have methods to measure pectin specifically as well. So For starch, sometimes you just want to know if you have starch or not, or sometimes starch is actually used as indicator in an assay, and we will use that when we do fat characterization. We're kind of going to use starch as an indicator, really. So the principle of that is iodine has an affinity, or amylose has an affinity to iodine, so you get blue color. That's an indication of the presence of starch through the interaction with amylose. Another form of qualitative analysis is looking at the structure of the starch granules. And the starch granules impact different functionalities of starch. The viscosity of starch, for example. So different sources of starch have different granular form of starch in its matrix. So microscopy is one way to look at that. But what we're going to focus on is the quantitative analysis of starch using enzymatic methods. So in order to determine total starch, we have to break it down. We're basically breaking down into singular monomers, which are, of course, the glucose monomers. So we want to break down starch totally into glucose. How can we do that? What enzymes do you think we can use? You've probably done that in your food chemistry. At least you talked about it. Yes, Evan? Amylase definitely is one of the enzymes you use. But let's look at this chart. So amylase is an endoenzyme, so it's going to break the alpha-1,4 linkages somewhere internal inside of the molecule itself. What we need to break it into monomers is to also have the glucoamylase in there. The glucoamylase is going to break 1 unit of glucose at a time. So the alpha amylase is going to chop it into smaller branches, smaller units. Then the glucoamylase is going to break it down into singular glucosides, glucose. So polonase sometimes is added to enhance the breakage of the alpha-1,6 linkage. It is specific to alpha-1,6, which is the branching point of the amylose and amylopectin. But that doesn't mean that amylase does not cut this. It also cuts the alpha-1,6. It has specificity to alpha-1,4 and alpha-1,6, but polonase is only specific to the alpha-1,6 linkages. So the Megazyme kit usually asks for amylase and, alpha amylase, specifically alpha amylase, and glucoamylase. And this will give me glucose. Other enzymes that can break up the starch is beta amylase. Beta amylase breaks dimers. So it gives you dimers or trimers. It really gives you maltose or maltotriose. So this is very specific enzyme that it only cleave 2 units or 3 units at a time. So both beta amylase and polonase cannot act on raw starch. So, or retrogradated starch. It has to be gelatinized starch. So keep that in mind for when we talk about gelatinization and retrogradation assay. So these 2 enzymes, beta amylase and polonase, the starch has to be gelatinized in order for them to act. All right. So back to this. So once we broke everything down, all the starch down to glucose, then I can quantitate glucose quantitatively using the glucose oxidase assay. So that's a double reaction, so 2-step reaction, where your glucose unit, if we reacted with glucose oxidase in the presence of oxygen, so it will be oxidized into gluconolactone, and we're going to produce hydroperoxide. So So the hydroperoxide is the product that we will use for the second reaction. So the hydroperoxide will oxidize a dye in the presence of peroxidase. So a peroxidase enzyme will use peroxide to oxidize a dye and produce an oxidized dye that has color, and that's what gets measured via spectroscopy. So we normally run a glucose standard, and we back calculate the amount of starch based on the glucose standard, and we use starch control as well. So degree of gelatinization and degree of retrogradation. So remember last time I asked you, can we use, or the time before last, can we use the same method to measure degree of gelatinization and degree of retrogradation? The answer was yes, and now I'm going to explain the method. How can one method be used to measure both degree of gelatinization and degree of retrogradation? So remember what I said about polymerase and beta amylase. They do not act on raw or retrogradated starch. You have to have gelatinized starch for these two enzymes to work. So you get your sample and you react it with polymerase that will debranch and beta amylase that will produce maltose and maltotriose. So if you're looking at degree of gelatinization, the more gelatinized the starch is, the more these two enzymes are going to work, the more maltose and maltotriose will be produced. And then to determine the amount of maltose and maltotriose released, you can measure the reducing sugar present. So these two are reducing sugar. So you can use one of the assays, the colorimetric assays that we talked about for measuring reducing sugar, like the Smoogie-Nelson method, for example. So the more reaction we get, the more reducing power we get. That means the more is the degree of gelatinization. On the other hand, degree of retrogradation is if you have high degree of retrogradation, you would not get maltose and maltotriose, or you will get little amount of that. So the higher the retrogradation, the minimal the amount of maltose and maltotriose that would be produced. So the result would be lower instead of higher. So the higher degree of gelatinization, the higher reducing sugars you're going to get. The higher the degree of retrogradation, the lower is the amount of reducing sugars that you're going to get. That's why the same method can be used for both. Okay. So moving on to dietary fiber. So here is a definition of dietary fiber, which you're all familiar. They're the edible part of the plant that cannot be digested and absorbed in the human small intestine. However, fermentation in the large intestine occurs. So that's kind of what defines dietary fiber, and it has multiple health benefits, and I'm not going to go into that. But in terms of the components of dietary fiber, you have polysaccharides, some oligosaccharides that are not digestible, like oligofructans is one, but also stachyose and raffinose. They are not digested. They are fermented in the large intestine. So two categories of the dietary fiber. You have the soluble fiber, which is mostly your pectin and any hydrocolloids or gums. These are the categories of food products that have high amount of soluble fiber. Insoluble fiber obviously is the material in the cell wall, mostly cellulose, hemicellulose. Some hemicellulose can be soluble, by the way. So mostly cellulose, hemicellulose, and your lignin, which is not a polysaccharide. It is a dietary fiber that is not polysaccharide. And resistant starch. So the starch that does not get digested. Remember the 4 levels of resistant starch. So given the complexity of your components, is it possible to analyze all dietary fiber in a single approach? No, it's just so tedious to analyze dietary fiber, and if you want to determine soluble fiber, you have to do certain approach, and if you do want to determine insoluble versus total versus just pectin, okay, it can get really complicated. In the past, crude fiber was a common method, but now it's no longer approved for claiming any fiber for human consumption. It's done a lot for animal feed. So crude fiber is basically a method that you would solubilize everything other than your fiber. So basically acid and alkaline extraction. So you would have a flask, you put your sample, you put acid, digest with acid, then digest with alkaline, and put it in a reflux system. That means you have a condenser and you have your flask on a hot plate. So you will digest it, and to enhance the digestion and make sure that your digesting acid and alkaline does not evaporate, they do not evaporate, you put a reflux unit, a condenser unit. So what happens there is you break with the acid and alkaline, you're breaking your protein, you're breaking your starch, you're solubilizing everything but the fiber. However, soluble fiber will be in this soluble portion. So this method only determines cellulose and lignin, really. It does not quantitate the other, maybe a little bit hemicellulose, but it does not quantitate your hydrocolloids, gums, or pectin. Same with the detergent extraction. So you use a detergent to solubilize everything, and your insoluble fiber, cellulose again, lignin, and some hemicellulose will precipitate. So both methods underestimate dietary fiber because it's not really measuring any of your soluble dietary fiber. So now the methods that is commonly and widely used for dietary fiber is your famous AOAC method, 991.43. Memorize this. No, don't have to memorize the number, but it is the most common method for dietary fiber. There is another integrated dietary fiber assay, which I'm not going to cover in this class today, because the integrated assay allows you to measure even the oligosaccharides portion, the soluble portion that are small molecular weight that you won't be able to precipitate and measure in this method. So what you start with, remember always, I would highlight this if you have your notes in front of you. Excuse me, you always have to make sure that you start with a relatively dry sample. So if your sample is flour, it's relatively dry, you don't need to pre-dry it. But oftentimes you have to pre-dry your sample, you have to defat it to get the fat out of the way. That's the first step. Oh, don't forget homogeneous sample, representative sample of the lot. That's always something that will hold you accountable for. And then you pre-dry and you defat, and then you want to get rid of everything but your dietary fiber. So what you would do in this case, it's an enzyme-based assay. So you would digest, after you gelatinize the starch, you digest with alpha amylase, and then you digest with the protease. Make sure you change the pH for the optimum for the enzymes that you're using. And then you digest with glucoamylase to make sure that everything, because alpha amylase is an endoprotease, so you would have large, probably longer chains of glucose. So you want to make sure you break them even more into monomers so they get all solubilized. So your protein and starch will be solubilized by the action of enzyme. At this point, you can take that sample that you solubilized, you can precipitate with ethanol, because dietary fiber, whether it's soluble or insoluble, will precipitate in ethanol. So even your soluble pectin and hydrocolloids will precipitate when you put them in ethanol. You wash, you dry. You always have to correct for any residual protein and ash that precipitated with your fiber. That means you measure protein and ash and subtract them from the total weight. Then you get your total dietary fiber. And usually we do ash by dry ashing, the way you did it in the lab, and protein by Keldal. Because with what we use to filter the dietary fiber will kind of block our crucible in the LICO instrument. Okay, if we want to determine how much soluble dietary fiber we have versus insoluble, because each one of them have different health impact, so we want to know how much soluble we have for a certain benefit versus how much insoluble we have, then we approach it differently. Instead of precipitating at this point, we filter and wash. So at this point, your soluble dietary fiber will remain with your solubilized starch and protein, and what would be precipitated on the filter is the insoluble dietary fiber. So here we go. So your residue, that means that stays on the filter, is your insoluble fiber, your cellulose, lignin, most of your hemicellulose. So I take that residue and I wash it with water and then alcohol, ethanol and acetone, to make sure that I wash more, nothing soluble in these will remain with your dietary fiber. So wash it even more from any residual amino acids or sugar. Just wash them off. And then still take those insoluble fiber on the filter, dry, and then you weigh it. So take the gram of that dried sample, and then from there, take one part of it to measure ash and part of it to measure protein. And then I subtract the amount of protein and the amount of ash from the weight, and then I get my total or my insoluble fiber amount. Whereas the filtrate, after the first filtration, so anything that goes through the filter and does not stay on the filter, contains your soluble fiber and your amino acids and sugars and all of those other soluble components. So here, what you do is, at this point, you take the soluble and then you add ethanol and filter, precipitate. So the ethanol will precipitate your soluble fiber, but will not precipitate, obviously, sugars and amino acids and such. So you get the solubles, you discard, you don't want them anymore, and then the precipitate is your soluble fiber. You do the same thing of washes with ethanol and acetone. You dry, you weigh, and then you take a portion, measure ash, take a portion, measure protein, and then you subtract these weights from the weight you got here, from N, and then you determine the amount of soluble fiber. In this case, you have the soluble fiber separate, you have the insoluble fiber separate. If you add them, you get the total dietary fiber. Okay. You can measure total insoluble and soluble fiber as well using the Englyst-Cummings method, which is a GC-based method. So in this method, you're actually looking at the component of your dietary fiber, the carbohydrate components, the singular units of what makes up your fiber. So you can determine I have 20% cellulose, I have 30% pectin, and I have the rest as hemicellulose or whatever. So you can actually determine the composition of the sugars that make up your dietary fiber. So to do that, you actually go through the similar steps of preparation. So you gelatinize the starch, hydrolyze it, and then digest with proteases to hydrolyze the protein. So similar steps. And then the remaining non-starch polysaccharides, you can separate them as soluble, insoluble, the way we did previously. But then there is a further step to look at the composition. You break them down into their free monosaccharides. So determine the concentration of each component of these fibers. We hydrolyze the glycosidic bonds. And we hydrolyze the glycosidic bonds by concentrated sulfuric acid. And then we get neutral sugars and we get the uronic acids from the pectin. So the neutral sugar you can derivatize. And like we talked about derivatization on Monday. And then you measure with GCFID. And then you can get the composition of the different sugars. Uronic acids, you use a colorimetric method to detect the amount of uronic acid and determine the concentration of pectin that way. Yeah, this is a very common method. We actually done it in our lab to characterize a new fiber from a new crop material that we're looking at. So in order to identify the components of a new crop material or new variety of, or a plant variety, this is one way of doing that, characterizing the fiber component. Okay. Pectin analysis, often you just want to determine the amount of pectin in your sample, especially if you want to determine for quality control measures and to determine if they've used only pectin as the source of gelatinization, gelation, for example, not gelatinization, sorry, this is for starch, as a source of gelation, and whether or not they used a different gelling agent. They're claiming it's, let's say it's a vegetarian product. You want to make sure that it has the pectin that they claim it has, not the gelatin, for example. So an easy way of doing it, especially for jams and jelly, since there's no other dietary fiber in there other than pectin, you just precipitate directly with alcohol and you just measure the amount of pectin that way. So that's easy. But if you have a complex food matrix, you have to go a different route to determine just pectin. In order to determine just pectin, you want to look at the, what can you do to determine the galactouronic acid in there versus the, so you have uronic and you have galactose. So uronic acid and galactose, the glycosidic linkage, you cannot break it by hydrolysis. It's very hard to break it. So instead of breaking the glycosidic linkages to determine the amount of galactose and uronic acid, you do a different way. You saponify with NOH. The saponification, as you already know, is breaking of esters. Now you know that from your GC lab. So the esters in this case are the methyl groups attached to the uronic acid component. So you have a methyl group with saponification is going to break off, and you will increase the amount of carboxyl groups or ionized carboxyl groups. And when you increase the amount of ionized carboxyl groups, then you can precipitate the pectin by adding calcium. So all of the galactouronic acids will be susceptible to interacting with calcium because we removed the methyl group. So they will react with calcium, then you will produce a precipitate, which is the calcium pectate. You can take that calcium pectate and measure it gravimetrically. Okay. So a practice for you, which you can do on your own and bring it probably Monday, would be a good time because you have a quiz on Friday, and for an extra +5 on this one. So since we're not going to run dietary fiber in lab, I just want you at least to practice the calculation of how you would determine the total dietary fiber. So here's your data. So look at it and let's decipher it together. All right. So we had high fiber cookie and we were analyzing the dietary fiber content by our one and only method. So you take your sample, and we usually use a crucible for filtering. So to filter the okay. Who had done dietary fiber? Did you do dietary fiber? Ali, did you do that? I know that we use certain shapes of crucibles. I don't know. And these have holes. And then we put the material, what is it called again? Does anybody remember the material we use to filter? Selenide? Anyway, material to filter. Instead of a filter paper, we use certain material to filter out everything and have your fiber remaining here. So because you're going to determine the amount of fiber in the crucible after filtration, you really need to take the weight of the crucible. And then we usually link it to a flask, and then here you have a pump to create vacuum. So you put your sample here, you create a vacuum, and then you help filtering. I think the suction is here, sorry, not here. Okay, so you solubilize everything using the enzymes, and then you filter at the time of filtration. When you add your alcohol and you want to filter, all the solubles will go here, and then you would retain your fiber here. So for insoluble, you measure the weight of the crucible before you filter anything in it, and then we have rep 1 and rep 2. And then we have another crucible for the soluble, because we're going to measure soluble alone and insoluble alone. And measuring the soluble, you take the filtrate from the, okay, I'm going to go back to remind you. So here when you filter, you have your solubles here, and here you have your residue. You take this soluble and filter it here, and you take that residue as well. So you take this soluble, you precipitate it and filter it alone, and you take this residue and filter it alone. So you need crucibles for soluble and you need crucible for insoluble. So that's why we have 4 crucibles, 1, 2, 3, 4, and we take the weight of each. And then for each of them, after the filtration step, you will have residue. So you weigh the crucible with the residue in it, and then the difference in the weight will be the weight of your precipitated fiber, whether it's soluble or insoluble. So you get that weight. And then for each rep, you subject it to either protein or ash. So this first rep was subjected to protein analysis by Kjeldahl, and you found you have 0.065 grams of protein after Kjeldahl analysis. And then here, you subject it to ashing, and then you get the weight after ashing. So that's the crucible plus ash. So you subtract the weight of the crucible. From here, you get the weight of the ash. So you subtract the weight of the crucible from this, you get the ash. So now you have the ash, you have the protein for the insoluble, and the same thing here. You have the protein and the ash. So the weights, the difference in weights of the fiber, you take out protein and you take out ash. And then you can calculate the amount of fiber. But then there is a blank. You have to have a blank that everything goes through without your sample. So you run everything to account for any weights or any dietary fiber that comes from whatever you're using in terms of reagents and chemicals and filters and what have you. So you do the same calculation, and you really need to subtract the blank from the sample. And here's the weight of rep 1 and weight of rep 2 sample. So this is the hint of what you need to collect in terms of data. So you need to take the average sample weight. So you'll use it at the end to determine percentage of dietary fiber. You calculate insoluble residue 1 and insoluble residue 2. You get the average of that for the blank and the sample. And you subtract value of blank from value of sample. And then you do the same to subtract blank protein from the protein of the sample, and ash also from the ash of the insoluble residue, the blank ash. And then you carry out this, your average insoluble minus protein minus ash that you get after correcting from blank, and here also after correcting from blank. By the average weight of the sample, you get the percentage. And then you repeat the same for soluble, and percent soluble and insoluble is total fiber. So just work on it just to get the experience of at least calculating for it. So next week, what we're going to do is determine total carbohydrate in beverages. So we're going to use the phenol sulfuric acid method. It's a very simple assay, but very dangerous. You're working with phenol, which is toxic, and you're working with concentrated H2SO4. Fun lab. So please come prepared by reading the chapters, and there will be a pre-lab quiz. Obviously, you need your lab manual. There's not going to be an addendum, and you need your laptops. We're going to do all the calculations in the lab, so the lab report will be easy. All you need to do is answer questions, because we will have time to do all the calculations in the lab. And Friday is the quiz. Please remember that all the material, all proximate analysis up until this lecture and the IR will be on the quiz. If you like, please come 10 minutes early so we can get started with the quiz and have time for some lecture. Okay, that's it. See you Friday.